Hello everyone. In today's lecture, I am going to discuss about two meters which are used for measuring electrical parameters. The meters are energy meter and potentiometer. And today's lecture has been organized in this fashion. So first, let us have a brief introduction about energy meter, and I'll be discussing one particular type of energy meter, and later potentiometer introduction will be given. And in DC potentiometer, there are different types, and one by one we will see. And at the end, we will cover AC potentiometer and its types. And let us start with introduction. So, what is energy? So, basically, energy means we know that it is a product of power into time, or otherwise, we can say that how much power consumed in a predetermined, in a definite time period. So, that is what energy. And in the available types, the induction type single phase energy meter is very common, and common unit which is used to measure energy is in kilowatt hour. And what are the basic differences between this energy meter and other analog type meters? So here in energy meter, there is no control spring and a pointer. So we will get to know how much energy recorded from the indicator, not from the pointer position. And here we are employing a brake magnet to control the movement of the disc. So these are the major differences when we compare energy meter with other analog meters which are used to measure voltage, power, current, etc. And here eddy currents here the eddy currents induced in the aluminum disc by the brake magnet due to the revolution of disc are utilized to control the continuously rotating disc. And if we take any analog type meters, we have to look into three important forces. First one is the driving force, second one is controlling force, and third one is damping force. So here, since there is no pointer involved, so here we don't need to worry about the damping part. So the other two forces need to be considered in single phase energy meter. So we will see how we are able to produce those two forces in energy meter in later slides. So before that, let us see the construction of induction type single phase energy meter. So this is the schematic sketch. So there are two magnets, namely M1 and M2, and as you can see that from the shape, so M1 magnet is called series or current magnet, which is in U shape, and M2 is shunt or voltage magnet, so it's in M shape, and its central limb there is a large number of fine wire, and whereas if you look at the M1, so it is wound with less number of heavy wire. So there is another name for these two magnets. Here the M1 magnet forms the current coil for the meter, and the M2 forms the pressure coil for the meter. So it is similar to electrodynamometer wattmeter construction. So how we are getting these particular names for magnet M1 and M2? So the current flowing through the load which is in series with the current coil, whereas the voltage across pressure coil will be the voltage across the load. So this is how we are getting the name pressure coil for magnet M2 and current coil for magnet M1. And here this is the bend, say permanent magnet is kept it over here, and there is a narrow gap between rotating aluminum disc and magnet. So this is going to give us a braking effect for the rotating disc. And for smooth movement of the disc is kept it over pivot arrangement. So as you can see here, and the same thing has been dictated over here. And since the M1 magnet wound with less number of wires, it is of heavy gauge wire, so with this it can withstand heavy currents. Now let us see how exactly the braking magnet is going to provide a braking effect for the rotating disc. So the Brake magnet, as I said earlier, it is of a C-shaped piece of alloy steel bent round the round to form complete magnetic circuit with narrow gap between the poles. So because of that, what will happen when there is a movement over a disk? When it through the magnetic field, it crossing the air gap sets up eddy currents in the disk. So which react with the field and exerts a braking field, braking effect. And this braking effect can be adjusted by adjusting the position of the braking magnet or by diverting flux from there. So as you can see in the actual energy meter here, for adjusting the position of or position or distance from the center, there will be a provision so by which we can easily adjust the position of the magnet. So this will help us to control the speed of the rotating disc. And let us see how we are able to get driving force here. So in working that is explained in detail. So here the sun electromagnet produce a magnetic field. It cuts through rotating disk and induces a circulatory eddy current, but doesn't in itself produce any driving force. Similarly, series electromagnet also does the same. So now the series magnet induces a flex, that is phi 1, namely phi 1. Shunt magnet M2 induces uh, another flex, that is phi 2. So these two flexes phi 1 and phi 2 interact together. It sets up the circulatory eddy current on the disk. Now the existing field and the produced eddy current interact together, that causes the disk to rotate. So this is how we are able to get driving force for the disk. So as the same thing is given in this last point in the working portion. So the reaction between these magnetic fields and eddy current sets up a driving torque in the disk. Okay, now let us see what are the common sources for errors in the energy meter. So incorrect magnitude of flux, incorrect phase relationship of flux, change in resistance of disk, changes in the strength of magnets, when there is a phase angle error due to power factor. So these are all some sources which causes error in the energy meter functioning. Now let us see how we are, what is the expression for driving torque and what is the expression for braking torque, and finally we will get how the speed of rotating disc is related to the energy. Now for that we are considering these nomenclatures. So V is the applied voltage and load current and phase angle of load, and IP is the pressure coil current, and delta is the phase angle between supply voltage and pressure coil flux. So later we are going to consider this as a 90-degree, and Z is the impedance of eddy current path, and the other two parameters are eddy EMF induced by fluxes phi 1 and phi 2. Here it is written as series and pressure coil. So based on these assumption, the net driving torque is given by driving torque TD is proportional to flux phi 1, phi 2. Phi 1 is the flux produced by series magnet, phi 2 is the flux produced by shunt magnet, F is the frequency, Z already is written over here, and sine beta, cos beta. So here what is beta? Beta is a phase angle between fluxes phi 1 and phi 2. And whereas alpha is phase angle of eddy current pass. So this is the net deflecting torque expression. Now we are going to bring power term in this expression. So let us see how it is. So here we assume that there is a phase difference between pi p and pi s, that is of delta minus pi value. So according to this, now the beta value is delta minus pi. So that is how it is written over here. And as I said earlier, how to introduce the power term, that is Vi cos phi. Let us see how it is. So the pressure coil is proportional to applied voltage, and the current flowing through the series magnet it proportional to phi s. So according to this, we can rewrite deflating torque into K2 is a constant term comprises all constant terms together, and instead of pi p we are writing V, instead of pi s we are writing I, and we have supply frequency and impedance sine of the phase difference into cos alpha. Now here for our convenience, what we are going to do, we are assuming that f, z and alpha are constant, and according to this what we are writing, the deflating torque is equal to the new constant v into I sine delta minus phi. Now here now we are going to write what is the expression for braking torque. So the braking torque is proportional to the steady speed of rotating disc. So according to that, we can write braking torque TB is equal to K4 into speed of rotating disc. In next slide, you can see that at steady speed, the driving torque must be equal to equal the braking torque. Then only the speed will rotate. The disc will rotate at steady speed. So based on that condition, we are equating braking torque expression equal to driving torque. So that is how we are getting this expression. And as I said earlier, the delta, there is a 90-degree phase difference. Assume that. Then when we consider the 90-degree, and the right hand side expression will become kvi cos phi. So as we know that vi cos phi is power. Now total number of revolutions made by the disc, it is over a time period, integral speed. So we are going to record a speed of rotating disc using a registering mechanism. And when we are substituting the derived term in this speed, and we can write that, so if delta is equal to 90-degree, that is the condition. Based on this condition, we can write that total number of revolutions made by the disc is equal to K into energy. So we know that energy is nothing but power into time. So here by integrating, we will be able to get power into time, that can be written as energy, and very common unit which is used for energy is in kilowatt hour. So in day-to-day life, many of us might have noticed the either analog type energy meter or digital type energy meter. So we can see that based on the speed of rotating disc, we will come to know that what kind of load we are using in the in the place. So when disc rotates very slow, it means only light load is used in the place, and vice versa when we are using heavy load in the place. And similarly, if it's this is in the case of analog energy meter. In digital energy meter, instead of rotating disc, we can see LEDs. So how fast the LED blinks will be the indicative of what kind of load we are utilizing in the place. Before let me complete this topic, let me summarize what are the concepts we have covered in this energy meter. So we have started with energy is power into time, and we have seen construction of the single phase induction type energy meter, and there are two magnets, one is series magnet and shunt magnet. Each will set up flex phi1 and phi2 respectively, and these two flexes will set up circulatory eddy current on a rotating disc, and this circulatory eddy current and existing flexes phi1 and phi2 interact together and gives us the driving force. And to control the speed of the rotating disc, we have a brake magnet. So the brake magnet will set up another eddy current. So that eddy current will interact with the brake magnet field, will give us a braking effect. And the speed of the disc can be controlled by adjusting the position of the magnet. And finally we have seen that how speed of number of revolutions made by the disk, it's related to the energy. So this is what we have discussed in energy meter. Okay, now let us start with the next meter. So that is a potentiometer. So in potentiometer can be classified based on the source of supply. That is suppose in the source or supply. That is either it is DC operated or AC operated. So based on that we have two broad category: DC potentiometers and AC potentiometers. We will see one by one. Before getting into detailed discussion on DC potentiometer, we will see what is the necessity of potentiometers first. So potentiometer is an instrument is designed to measure an unknown voltage by comparing it with a known voltage. So because of this can be used to calibrate voltmeter, ammeter, wattmeters, even energy meters can be calibrated using this potentiometer. So we will see these applications later part of the discussion. Here, for comparison, what we will be doing, we will be using the standard cell or known voltage as a reference. So here the advantage of potentiometer is makes use of balance or null condition. Because of that, no current flows and hence no power is consumed in the circuit containing the unknown EMF when the instrument is balanced. So since potentiometer measures voltage, it can be used to determine current simply by measuring voltage drop produced by unknown current passing through a known standard resistance. So this is one of the application part. So we will have detailed discussion on this later. As I said earlier, the potentiometer is extensively used for the calibration of voltmeters and ammeters. Even wattmeters can be calibrated using potentiometer. Now let us start with a very basic type of DC potentiometer. We call that as a basic slide wire potentiometer. This is the basic schematic sketch of that, and let me tell you what are the key components of this type of potentiometer. So here there is a slide wire of length 200 centimeter. It is uniform. It has a uniform cross section. It means we can consider that 1 ohm per centimeter. So totally this slide wire can offer 200 ohm resistance, and there is a DC source, that battery source, and there is a rheostat. By adjusting the rheostat we can adjust the working current for this instrument, and there is a standard cell or a known voltage. The typical value for this cell is 1.0186 volt, and unknown EMF which is to be measured. And here there is a galvanometer. So using this we will read whether we have achieved a null condition or not. So for doing that, whenever we press this key K, the galvanometer reads 0. It means we have achieved a null condition. At the null condition, whatever potential drop across this slide wire will match the either unknown EMF or standard cell EMF according to the mode what we have selected. Say example, if calibrate mode is selected, if galvanometer reads 0, it means the potential drop across the slide wire with respect to position of the slide contact, that potential matches the standard cell. So this is how this instrument is going to help us to measure unknown EMF. Okay, so this is the basic construction and the major components of the basic slide wire circuit, and the same thing is being presented in this slide. Now when we are going to use this DC potentiometer to measure unknown EMF, first we have to connect the mode, we have to connect the galvanometer to calibrate mode. Later we will connect it to operate mode. So what exactly we are going to do when the mode is calibrate? So we are going to do the process called standardization. So let us see what is the standardization. Already I have mentioned that the slide wire has a uniform cross sectional area, and hence it has uniform resistance along its entire length. So we have seen that in the circuit. So the length of the wire is of 200 centimeter. So it means the total distance of that wire is 200 ohms. So because of that, what advantage we are getting? Since the resistance of slide wire is known accurately, the voltage drop along slide wire can be controlled by adjusting the value of working current. So the working current can be adjusted using the rheostat RH. So the process of adjusting the working current so as to match the voltage drop across a portion of the sliding wire against a standard reference source. Here we are considering the standard reference source as 1.0186 volt. So when it matches, by adjusting that working current, we say that we have done the standardization. So standardization is basically a process of fixing the working current for the instrument. And the important requirement is that once we have fixed the standard working current, that should not be altered when we are going to operate the instrument under operate mode. So this is very important here. And let us take one example to understand the standardization process in a better way. So what's the little procedure is given. So here this is the known to us already. So resistance of the wire is of 200 ohm and the standard cell is of 1.0168 volt, and we are throwing the switch S to calibrate position, and we are placing the sliding contact at distance 10186 centimeter. So according to this distance, the resistance of the wire according to this point it's 101.86 ohm and standard cell we have of 1.086 volt. So by using this resistance and this potential, we are able to calculate how much will be the working current. So it is of 10 milliampere. So what we are going to do, after placing the sliding contact at this distance, when we press this key, and we will read whether galvanometer reads 0 or not. If galvanometer does not read 0, and we adjust the rheostat till galvanometer reads 0 when we press the key. So at that when we achieve that null condition, so it means that the potential across this distance matches the standard cell voltage. So based on that, if you do the calculation, so we will get a working current of 10 milliampere. So this process is called standardization. Now, if you look at similarly, after completing the standardization process, we will throw the switch S2 unknown EMF, and we should not touch the position of rheostat because we have fixed the working current, and we will adjust the only sliding contact to match the potential E1 with the potential E. So to read that, when we press the key, galvanometer if reads 0, it means we have achieved we have made potential E1 is equal to E. So this is how we will be able to measure unknown EMF accurately using DC potentiometer. Now let us take modified version of the basic slide wire potentiometer, that is called laboratory type, because the basic slide wire arrangement that cannot be used as such for laboratory purpose. So the other name for this instrument is Crompton's potentiometer. And let us see the basic diagram of this type of potentiometer. In basic diagram, we have seen that there was only one slide wire, but here it is not so. There are two slide wire. One is called main dial switch, other one is circular slide wire. The resistance, total resistance offered by this main dial switch of 150 ohm. So here you can see that the dial switch of 15 steps of 10 ohms, therefore total resistance 150 ohm. So here as you can see, there is a scale already marked over the dial switch starting from 0 to 1.5. It is nothing but volt. So we can measure voltage from 0 to 1.5 volt using this only main dial switch. Similarly, using this slide wire, we can measure up to 0.1 volt. So, but commonly when we add, because since this main dial switch and slide wire is in series, the total potential what we can measure using this arrangement is 1.6 volt. And what are the other components which are present in this type of potentiometer we'll see. As it is in the basics arrangement, there is a rheostat. By adjusting this, we can fix the working current by doing standardization. And here there is a key, and in series with that there is a high value resistance. It will protect the galvanometer from high current, and there is a shorting key. This will be used as soon as galvanometer approaches null position, by which we can increase the sensitivity of galvanometer. And there are two modes, calibrate and is mode, like just a basic slide wire arrangement, and standard cell is also placed over here. And there are terminals to connect unknown EMF. And here there is a double throw switch. Using this we can connect either standard cell or unknown EMF accordingly. Now let us see what are the steps are used when making measurements with the above potentiometer. As I mentioned, the combination of main dial resistor and slide wire is set to standard cell voltage. And second step, the switch S is thrown to calibrate position, and the galvanometer key is pressed while rheostat is adjusted for zero deflection on the galvanometer. So what is the name for this procedure? It's called standardization basically. And as I mentioned, in the circuit there is a protective resistance, and it is kept it in the circuit in the initial stages so as to protect the galvanometer from being getting damaged from heavy current. And third step, as the balance or null point is approached, the protective resistance is shorted so as to increase the sensitivity of the galvanometer. And final adjustments are made for zero deflection with the help of rheostat. This completes the standardization process for the potentiometer. And next step, after completion of standardization, the switch S is thrown to operate position, where we are connecting the unknown EMF which is to be measured with the protective resistance in the circuit. Only when galvanometer approaches null balance, only that time we will short circuit the protective resistance, by which we are able to increase the sensitivity of galvanometer. But whenever we are going to start the fresh measurement, we have to include a protective resistance in the circuit to protect the meter. And fifth point, as the balance is approached, the protective resistance is shorted, and fine adjustments are made to obtain the true balance. And the value of unknown EMF is read off directly from the settings of the dial adjust slide wire, because already in the basic circuit diagram we have seen that in the dial itself there is a scale to read the voltage value. So from main dial we can read up to 1.5, and from the slide wire we can read up to 0.1. So together we'll get 1.6, and there are fine divisions are there, so we can read voltage values very accurately. So we have taken that the standard cell voltage of 1.0186 volt. So if you want to set that here in the main dial, we have to set switch at 1, and for the remaining thing we have to set 0.0186, we have to set in the slide wire. So here according to this position of the slide wire, approximately one can understand that this is 1.3 volt plus this is 0.1. Here some assume that if it is a something around 0.6, so sorry 0.06, so it is together 1.36 volt according to this position shown in the diagram. So this is how we can measure the magnitude of EMF which is connected either at operate mode or calibrate mode. And the seventh step, after doing this, again we will check the standardization of the potentiometer by returning the switch S to calibrate position, and the dial settings are kept exactly the same as in the original standardization, that is at 1.0186 volt position. And we will check it again when we press this key. If galvanometer reads 0, if it's fine. If it is not, again we have to do that standardization process again. So with this With this, the standardization process, the completion of measurement, this potentiometer is a form of Crompton potentiometer. Now, next what we are going to do, this basic arrangement is shown only for one particular range. Let us see how this DC potentiometer can be used for more than one range. So here we are going to restrict ourselves only for double two ranges, that is called duo range. Though the name is multi-range, here we are restricting ourselves only for two ranges, that is called duo range type potentiometer. Here you can see that the arrangement is similar to Crompton potentiometer. Here in order to get a second range, here we are including resistors R1 and R2. So the presence of resistors R1 and R2 gives us option to measure voltage in another range also. So here, just for our discussion, we are considering the range 1 as x1 and range 2 as x.1. So from the scaling one can understand that the difference between two ranges, it's of 1/10. Say example, at range 1 if we can measure 10 volt, and at range 2 we can measure 1 volt. So that is the basic idea. And here the potential across the point A and C is shown as potential EAC, and we are trying to match this with the potential across the main dial and slide wire. And other components are same as the basic arrangement. Here also we have a key and protective resistance and galvanometer and calibrate and operate mode. Now here in this multi-range potentiometer, the key requirement is that irrespective of the range, the current drawn from the battery should be constant. That is total current. Total current is the current drawn from the battery, whereas the current what is exactly flowing through the slide wire, we are going to name it as IM and IM dash. So IM is the when it is at range 1, IM dash is the when it is at range 2. That is how we are going to continue our discussion. So same thing is shown over here. The two ranges are obtained by using two resistors R1 and R2 and a range selecting switch S, and the total resistance of measuring circuit is Rm. So here in this circuit, the total measuring circuit resistance when it is at range 1, 150 plus 10 ohm, 160 ohm, and this will be different when it is connected at range 2. So that time R1 and R2 will be included into the circuit. So we will see what exact how much is the value of Rm and R1 R2 value. So later part of the discussion. So the main dial has 15 steps. So that is what I have said now. And the measuring current, what we are going to set here when it is in calibrate mode is of 10 milliampere. So this is possible if the standard cell potential is 1.0186 volt. And here in the last line you can see that the resistance of main dial and slide wire are in series basically according to the connection. Now let us take the equivalent circuit with respect to range 1 and range 2, and we are going to see how we are able to maintain the total current IT as constant irrespective of the range. So EAC is the potential already was shown in the according to the circuit diagram, and RM is the measuring resistance, and see here IM dash is the current measuring current which is flowing through the measuring resistance when range 2 is selected. And let me hide this for being okay. Now here let us take the range 1. According to range 1, the R1 R2 is in series. According to range 1, you can see that when range 1 is selected, so it's left it open, so automatically this resistor R1 is in series with R2, and this series combination will be parallel with main dial resistor and slide wire. So together it is named as Rm. So that is what shown in the first part of this circuit diagram. And similarly, when range 2 is selected, according to that connection, Rm will become series with R2. Now the total measuring resistance is Rm plus R2. So this is different from first part of the circuit, and the parallel resistance is only R1 here. Now one more information what we can see from the circuit is that according to the first range, the measuring current is only Im. In second range, measuring current is Im dash. So we have 1/10 scaling factor. So if Im is 10 milliampere, Im dash will be only 1 milliampere. So that is how we are going to maintain IT as constant irrespective of the range. Now let us have some detailed discussion on this equivalent circuit. Since our primary objective is to maintain the total current constant, so we are using this equivalence. So when we are reducing the left hand side circuit and right hand side circuit, basic simplification, so we'll be able to end up like this, and by cancelling out the common terms, and finally we are getting the resistor R1 is equal to Rm. So here in this case, assume that if the range 1 is selected and Rm value is 160 ohm, so R1 is 160 ohm according to range 1. So like this we have to calculate what is the value of another resistor which is present in the circuit, that is R2 value. So we will see how much it is. Now current through the measuring circuit on second range, 0.1 range, should be 1/10 of the current in the measuring circuit. So that is how we are writing this Im dash equal to 0.1 times Im value. And how much is Im value? So Im is the EAC divided by Rm value. So EAC it's known to us, so it won't be a problem to find how much will be the Im value. And we are writing Rm is modified into Rm plus R2 according to second range, and 0.1 times Im value is equal to EAC upon Rm plus R2 value. So from 1 and 2 we are able to find value of R2 as 9 times Rm value, that is same as 9 times R1 value. So if for a taken case, if R1 value is of 160 ohm and 9 times of that value will be the our R2 value. So the same thing is shown here. So these two are equal, it is 160 ohm, and R2 is 9 times of that value, it is 1.44 kilo ohm. So according to this resistor value, if we calculate the total current IT which is drawn from battery, it will be of 11 milliampere. So this is how, by choosing proper value for R1 and R2 irrespective range, we are able to maintain constant current drawn from the battery. Now let us see very common applications of DC potentiometer. At the introduction level itself, I have mentioned that primarily these are used to calibrate voltmeter, ammeter, even sometimes this can be used to measure unknown resistance. Let us see how potentiometer can be used to calibrate voltmeter. So this is the basic arrangement. Here there is a provision for making coarse adjustment and fine adjustment. So the coarse adjustment, we can approach the major scale as quickly as possible, and fine adjustment is used to adjust the pointer to make the pointer to exactly coincide with the major scale or the fine divisions. So for that only we are having fine adjustment and coarse adjustment provision, and the voltmeter what is shown here, connected here, which is to be calibrated. And right now according to this arrangement we are going to use 150 volt range, and there is an additional equipment called voltage ratio box or volt ratio box is used while using this potentiometer for higher voltage application. So we will see the working of this voltage ratio box after discussing various applications of DC potentiometer. And let me hide this. And you can see here, so there are different levels at the input side of voltage ratio box. Start from a common, that is 0, 15 volt, 75, 150, 300 volt. Right now we are going to connect a voltmeter which is in the range of 0 to 150 volt only, and the output of the potentiometer, output of voltage ratio box is connected to the potentiometer. So basically voltage ratio box, it's like a potential divider and it's acting like a stepping down. Why we need this voltage ratio box? So we know that in potentiometer, what is the maximum measuring range is possible. So from main diode switch and slide wire together, we can measure only up to 1.6 volt. But if you want to calibrate voltmeter for a voltage of 150, we cannot give 150 volt directly to the potentiometer. So we have to step down, which is compatible for a potentiometer. For that only we are using a voltage ratio box. Okay, now how exactly we are going to calibrate the voltmeter? So it's very simple. When we connect the source, when we vary the voltage, in voltmeter we'll read some voltage, and we are going to compare whether the voltage read off from the voltmeter is matches the output from the potentiometer. If both of them are exactly same, it means the meter which is under test, it's working perfect. If it is not, what we will do, we will take this meter to the manufacturing unit again, and required changes will be made on the meter. So this is how we will be calibrating the voltmeter. And next application, calibration of ammeter. So here also, here we have coarse adjustment and fine adjustment. So to make the pointer to coincide exactly with the major divisions, we have this provision. And for proper operation of this potentiometer, we need a very stable DC source. It's similar to the previous application. And here there is a ammeter which is to be calibrated, and along with that there is a standard resistance. So the drop across the standard resistance used is connected to the potentiometer. So from whatever drop appearing over here can be read off directly from the potentiometer. Okay, now how exactly we are going to use potentiometer here to calibrate the ammeter? Let us see that. Now there is a current flowing through the ammeter. It reads some magnitude, say example 1 ampere. The same 1 ampere is going to flow through this standard resistance. So since current is known already to us, and it will not be that difficult for us to calculate how much is the potential. Now this calculated potential should match the calculated potential across standard resistance should match the potential output of a potentiometer. If both of them are equal, then the ammeter is working perfectly. So this is how we will calibrate the ammeter. And one more application, how DC potentiometer can be used to measure unknown resistance. So here also, with the stable source, we have fine adjustment and coarse adjustment provision. And again there is a ammeter to read how much current flowing through the two resistors. There are two resistors. S is the standard resistor, that is a known value, where another resistor is called R, which is the unknown value, which is to be measured. And there is a switch. So at a time, either drop across S or drop across resistor R is connected to the potentiometer. So simultaneously we cannot connect both the values, it's obvious. And assume first we will connect the potentiometer to the position 1 1 dash, and with respect to that position we'll be able to measure how much is the drop across R, say that is VR value. And we will throw the switch to 2 dash position, and we will measure how much is the drop across S using potentiometer. Let us say that is Vs value. And by using simple concept, directly we will be able to calculate how much is the R value. So we cannot directly read R value from this measuring arrangement only we can calculate. So here potentiometer is used only to measure potential. Using that potential we are able to calculate the magnitude of unknown resistance. And even this can be used to measure power also. So it's shown over here. And here voltage reading of potentiometer when connected to the standard resistor, and voltage VR is when connected across unknown value. So that is a load. That is load. VR is nothing but when connected across voltage ratio box, that is load. And here you can see that in this voltage ratio box, the voltage range what is selected is 300 volt, whereas in the first application, that is calibration of voltmeter, we have shown that it was used at 150 volt. So similar concept is used here to calibrate the, or sorry, to measure how much power. And here you can see that the current through the load I is VR by S, that is the standard value. Voltage across the load, it's given by, it's a scaling factor basically. K is the multiplying factor of voltage ratio box, it is fixed already. K into VR, that is VR is the drop across the voltage ratio box, and power consumed V into I. V into I, just by multiplying these two we'll be able to measure how much is the power. So let me show that circuit again. So there is a standard resistor, there is a load, actual load, and there is a voltage ratio box. So first we will connect standard resistor, and later we'll connect the load, and from this we will be able to calculate two values I and V, and product of these two will give us the power. So since we are doing all these measurements and calibration calibrations by comparison, that is we are comparing the actual value with the standard value. So the accuracy of calibration and accuracy of measurement is very high when we are doing this with potentiometer. Now let us see how voltage ratio box is working. So as I mentioned earlier, voltage ratio box is basically a potential divider. So there is a total resistance of 30k. So this is 300 volt range, this is 150 volt range, 75 volt, and there is a common terminal. When we connect the voltage to 75, so it means we will be able to get maximum only 75 and respectively. And here at the right hand side, if you see, there is a resistor value of 750 ohm that is considered. So the drop across that 150 ohm is given to the potentiometer for measurement purpose. Even sometimes minimum value is 150, even it can be of 160 ohm also. So if it is 160, it's very simple. We will consider only 160 ohm, and correspondingly what voltage we will be getting from that, it is 1.6 volt. Now let us take a simple example. Suppose the voltage to be measured is connected between common terminal and 300 volt. If reading of potentiometer is 0.826, then what is the actual input we have connected, that is unknown voltage. It's very simple calculation. For 300 volt from potentiometer we can read 1.5 volt. If potentiometer reads 0.826 volt, then how much is the actual input voltage? It is a 165.25 volt. So using this simple calculation, we can easily relate potential output of potentiometer with the actual unknown voltage what we have supplied through voltage ratio box. So this is how DC potentiometers are used in calibration as well as in measuring unknown resistance and unknown power. Now let us move on to next one. Before that, there is let us take one simple numeric example to understand this DC potentiometer concept in a much better way. So let me read the question. A simple slide wire is used for measurement of current in the circuit. the voltage drop across a standard resistor, that is S. Normally that is a notation we have used in almost all the circuits. zero point 0.1 ohm is balanced at 75 centimeter. Find the man read of the current if the standard cell EMF of 1.5 volt is balanced at 50 centimeter. So what is the solution for this? So voltage drop per unit length. Voltage drop per unit length is given as 1.5 volt divided by 50 centimeter. It is of 0.029 volt per centimeter. And similarly, voltage drop across 75 centimeter length. So already we have a value per centimeter voltage drop value, and using that we can easily calculate how much it will be for 75 centimeter, that is of 2.175 volt. Therefore current through resistor is I divided by this 2.175 volt divided by 0.1, it gives 21.75 amperes. So this is how we can use the potentiometer to measure the current through the resistor value. Now for reading purpose, there are a few more solved problems are given in the presentation, so you can go through this for understanding the uh, purpose of this DC potentiometer much better way. So I just leave it to you as a self-study part. Okay, now we are coming to the next type, that is AC potentiometer. So since the DC potentiometer is an accurate and a more versatile instrument, this can be used even for AC also. So when we are going to use this potentiometer for AC, so we need some minor modifications in the existing circuit. That is, in DC potentiometer we are using a basic galvanometer. So the basic galvanometer cannot be used for AC. So we have to replace that basic galvanometer with vibrational galvanometer, and similarly we cannot use a normal ammeter to measure how much is the working current which is flowing to the meter. So instead of using normal ammeter, we will be using a transfer type instrument. What is transfer type instrument? Transfer instrument means the instrument can be used for both AC as well as DC. So the whatever reading we are getting under a DC source, same value can be obtained even when we are measuring under AC source. So here it's shown that the most important difference between DC and AC potentiometer is that whereas in a DC potentiometer only man read of the unknown EMF, we don't bother about the phase in the DC obvious, and whereas here in AC potentiometer when we are considering the man read of unknown EMF, we have to also see what is the phase of that also. So this is another major difference between DC and AC potentiometer. And here the AC potentiometer is a complicated instrument, and there are certain important factors which must be considered for its operation. So the necessary requirement for balance in an AC potentiometer is the equality of voltages being measured at all instants. This requires equal phase and magnitude at all instants. So it means we need a standard source or stable source is primary requirement for this AC potentiometer. And as I said, here we are using a special type of galvanometer that is called vibrational galvanometer, which is a tuned device, is usually used as a detector. That's what detector is, nothing but for to see whether we have achieved null balance or not. And finally the ratio of two voltages, unknown voltage and voltage across the potentiometer, may be determined with the high degree of precision and accuracy. So here this is one of the primary advantage of accuracy and precision, is primary advantage of measurements with potentiometer. And like DC potentiometer, even AC potentiometers need to be standardized. So what we do, when we are going to standardize the AC potentiometer. So the AC potentiometers are made direct reading type, that is readings are read off directly from the dial settings. Like DC potentiometer, the standardization is done with the help of standard DC source, that is a standard cell or Zener source and a transfer instrument. Already I have mentioned about that. What is transfer instrument? The transfer instrument is usually an electrodynamometer milliammeter, because here we are using only ammeter, so we are particular about milliammeter. So consider that its response the electrodynamometer ammeter is considered that its response to alternating currents is the same as its DC response. So such an instrument can be calibrated on DC and then brought to the same settings on a AC source. So instead of electrodynamometer ammeter, even we can use a thermocouple type of instrument as a transfer instrument, but generally we are using electrodynamometer type meters as a transfer instrument. Okay, let us say what are the two types in AC potentiometer. One is polar type, another one is rectangle or rectangular type. So in polar type, there will be a dials. From one dial, we can directly read what is the magnitude of the unknown EMF, that is V. From another dial, directly we can read what is the phase of that unknown EMF. That is what polar type. Whereas in rectangular type, here also there will be two dials. So from one dial we can measure in phase component voltage V1, that is along x-axis V1, and another voltage called quadrature phase voltage, that is V2 along y-axis. So using these two voltages we have to calculate what is the magnitude of unknown EMF V and what is the phase angle of that the same. So it is square root of V1 square plus V2 square, and angle theta is shown over here, tan inverse of V2 by V1. So here from polar type we can directly get the magnitude and phase angle from the dial position, whereas in rectangular type we will get only potential value. From the potential value we have to calculate the magnitude and phase angle of unknown EMF. Here there are two types. Here we are going to we have to discuss dry scale. Dry scale, it's not shown displaying here. So dry scale polar potentiometer. This instrument consists of a potentiometer of ordinary DC type, except that the resistance coils are non-inductively wound and the following auxiliary apparatus is used. So let us see the construction. So this is how one of the component looks like. So what are the auxiliary apparatuses are used here? So the apparatus is phase shifting transformer, which consists of a laminated silicon steel rotor, and there is a stator winding which is divided into two halves, stator winding 1 and stator winding 2, and here the stator winding 1 is directly connected to the supply and stator winding 2 is connected through resistor R and C. So here there is a small air gap between the rotor and the stator. When current flows in the stator winding, a rotating field is produced, thereby inducing an EMF in the rotor winding. So the rotor can be adjusted for any required angle. The steel rotor can be adjusted for any required angle. The phase displacement of rotor EMF being equal to angle through which the rotor has been moved from its zero position. And there is a scale and a pointer provided on top of the instrument to indicate angle through which rotor has been moved from its zero position. So the scale is graduated both in degrees and cosine of the angles. That means from the rotor on top of this there will be a pointer. So the pointer will indicate what is the phase angle of unknown EMF. Similarly, there will be another apparatus, that is slide wire arrangement. From slide wire arrangement, we will be able to measure what is the magnitude of unknown EMF. Now, in what is the use of RNC which is present in this phase shifting transformer? Let us see that in phase shifter it is only necessary to have two separate windings displaced by 90 degree in phase on the stator winding. So both stator winding 1 current and 2 in magnitude both should be equal, but they should be separated by 90 degree. So to get that 90 degree phase displacement, we are adjusting R and C which is present in series. Uh, and the values of R and C are adjusted until the currents through the two windings S1 and S2, that is stator winding 1 and 2, are equal and are 90 degree displaced from each, creating a uniform revolving field. Now in this slide let us see how the resultant EMF induced in the rotor, it relates to the phase displacement. So there are two potential with respect to stator winding 1 and stator winding 2, E1 and E2. There is a 90 degree phase difference which is possible by adjusting resistor Rn, capacitor C. So at the end we are getting these two, and sum of these two resistance E1 and plus E2, when we add these two together, finally we are able to get Ki sin omega t minus theta. So the above relation shows that the rotor EMF has a constant amplitude, but the phase angle is given by the rotor position theta. So constant magnitude is Ka value, and the phase component of this induced EMF is proportional to the theta value. So by which we can comment that the induced EMF in a rotor is only variable with change in angle of rotor drum. It's constant with respect to magnitude. So this is how we are able to measure phase angle of an unknown EMF. And with respect to transfer instrument, how we are going to use this AC potentiometer. The basic connection diagram is shown over here. So here we are not going to use a normal galvanometer when we are operating under AC current. We will be using vibrational galvanometer, and ammeter is of transfer type milliammeter, and there is a slide wire arrangement, and here you can see that there is a DC source for standardization, and this will be connected to unknown EMF when we are operating under when we are using operate mode. And here important thing is, since we are going to use a vibrational galvanometer in the as a detector, this must be carefully tuned to give resonance at the frequency of the circuit under test. There is a small resistor R is a shunting resistor for the reduction of the range of a potentiometer, and when this shunt is put in the circuit by the switch S1, resistor R is simultaneously connected in series with the slide wire circuit, in order that resistance of the working portion of the potentiometer may be maintained constant. And as like other normal potentiometer, there is a rheostat R for adjustment of slide wire current, that is working current. And as I mentioned earlier, there is a precision ammeter that is of transfer type in nature. And here when we are going to measure unknown EMF, first we have to do the standardization. When we are about to do the standardization, we will replace the normal vibrational galvanometer by a de-arsenal galvanometer, and the standard DC source is connected in place of AC source, and working current will be adjusted, and this is how we do the standardization. And at the end of the standardization, what we will do, we will throw the switch S to the alternating supply side, that's the AC side, and standard cell and basic de-arsenal galvanometer being replaced by the AC source and vibrational galvanometer respectively. Now the stator windings of the phase shifter are then adjusted to exact quadrature by means of a variable resistor and capacitor, this being adjusted until the alternating current in the slide wire is constant for all positions of the rotor, and balance of the potentiometer is obtained by successive adjustment of sliding contacts of the slide wire circuit and of rotor of the phase shifter. Finally, the readings of the potentiometer dials and slide wire at balance give the magnitude of voltage being measured, while the reading on the scale of the phase shifter gives the phase of the voltage being related to the supply voltage. For accurate result, it is necessary that the voltage and frequency of the supply are steady, and that waveform of the voltage is reasonably sinusoidal. So by this we are able to get direct reading type AC potentiometer. And what are the major applications of AC potentiometer? Like DC potentiometer, this can be used to calibrate voltmeter, ammeter, to and another application to test the watt meter and energy meters, and even this can be used to measure self reactance of the coil. So let us see how this can be used to measure self reactance, because other applications we have discussed in DC potentiometer itself, so we are concentrating only on the fourth application. So here in this circuit there is a standard stable source, there is a standard resistor coil under test, and either coil or standard resistor will be connected to potentiometer using this selector switch. When standard resistor is connected, from the potentiometer we will get magnitude of that same and phase angle of that, and when we are connecting the coil to the potentiometer we will get corresponding potential and phase angle. So from this the current through the coil, current through, simply easily we can calculate. That is the magnitude divided by the known standard resistance value, and impedance of the coil is given by voltage across the coil divided by current flowing through the coil. Just by doing simple substitution we will get this expression. From impedance we will can calculate the resistance of the coil, z times cosine of phase difference coil minus standard resistance phase angle value, and resistance of the reactance, this is supposed to be reactance of coil, is given by impedance into sine of phase difference. So using these expressions, after measuring magnitude of voltage and phase angle of standard voltage and unknown coil voltage, we will be able to measure reactance of the coil. And there is a one solved example to understand how exactly we can measure inductance of the coil. So there are two potential values which are given with respect to standard resistor, and with respect to coil there are two voltages. With respect to coil, it is this is the potential given, and with respect to test coil there is another potential. Now we are supposed to calculate the I value. It's straight away, since there is a voltage ratio box, the obtained result should be multiplied by 100. It's a scaling factor, and already we have expression for reactance of the coil and resistance of the coil. So directly we can calculate, use that formulas to calculate the values, and finally we can find how much is the inductance of the coil. It's x upon 2 pi f will give us the how much is the inductance. So for all these concepts whatever so far I have discussed, I have referred this material, even all the images are taken from these only. So as a quick summary, so first we started with energy meter introduction, and we have seen very common popular type, that is single induction type energy meter construction, and corresponding deflating torque, braking torque, and speed of disc derivation part. And later we have started potentiometers. First we had a discussion on DC potentiometer concepts, and we have seen different types of the same, and we have seen what are the applications of DC potentiometer, And finally, we have discussed AC potentiometer, and in AC potentiometer, we have seen basic difference between AC and DC potentiometer, and we have taken one type of AC potentiometer, that is dry scale potentiometer, that is of polar type, and we have seen what are the auxiliary apparatus which are required to operate that instrument. And finally, we have taken one simple example to understand how exactly potentiometer can be used to for a particular application. Okay, so with this, this session ends. So thank you for listening.